Budget your retries, not just your code. By the end, you will have a clear Python pattern that stops wasting time, limits monetary cost, and spaces retries with sensible backoff. You will know how to enforce a maximum number of attempts, a total time budget, and a capped exponential backoff. I'm Professor Pi, teaching AI engineering and LLM systems from basics to advanced in simple Python. Retries are everywhere. You call an unstable API. You get transient failures. Naive retry loops either hammer the service or quit too early. Retry budgeting treats retries like a resource. Success means meeting service reliability goals without blowing time limits or cost constraints. Compared to blind retries, budgeting gives predictable latency and predictable expense. The downside is extra control complexity, but that complexity pays off with fewer surprises in production. At a high level, this is simple. Decide 3 limits. 1. A maximum cost or attempt count. 2. A maximum total time you are willing to wait. 3. A backoff strategy to space retries. Imagine trying an API up to 5 times, but stopping after 30 seconds total, and doubling the wait each try up to 8 seconds. That mix gives you both speed and safety. We will build a small set of examples that progress from a fixed attempt limit to a combined max cost and max time approach with capped exponential backoff. Now let's start with the simplest attempt limit example. This snippet retries up to a fixed attempt limit until it succeeds. This snippet shows the basic loop that tries an operation and stops after a fixed number of attempts. It is the cleanest introduction to retry budgeting because it enforces a cost cap expressed as attempts. If you lower the attempt limit, you reduce potential cost and reduce tail latency, but you also raise the chance of giving up too early. If you raise the limit, you increase success probability at the expense of more time and possibly more expense. This is the foundation you will extend with time and backoff controls. Next, we add a time budget to prevent long waits. This example enforces a time budget using a fixed per try duration. This example wraps each try with a simple deadline check, so the whole process never exceeds the allotted total time. It shows how to measure elapsed time and abort further retries when the remaining budget is too small for another attempt. If you tighten the total time budget, you ensure faster failure feedback. If you loosen it, you give more room for retries. This pattern is critical when downstream SLAs or user experience demand predictable maximum latency. Now we compare fixed waits with exponential backoff. This code compares total waiting time for fixed and backoff delays. This piece walks through computing the cumulative sleep time for a fixed delay versus exponential backoff across the same number of tries. It helps you see why exponential backoff favors quick recovery for early retries, but limits overall waste by growing waits later. Changing the base delay will change the pace of retries. A larger base makes early waits longer. A smaller base makes early retries more rapid, but can increase request rate against a stressed service. Next, we cap backoff to avoid runaway waits. This snippet caps exponential backoff to prevent overly long waits. This shows the classic backoff cap pattern, where the exponential sleep grows but is bounded by a maximum wait. The cap prevents pathological waits on networks that recover slowly, and it keeps user experience reasonable. If you set the cap tight, you avoid long sleep intervals but may end up retrying more often. If you set the cap high, you give slow systems more breathing room, but increase tail latency. This is a pragmatic balance you will tune for your service requirements. Finally, we combine everything into a budget-aware strategy. This code combines time and cost budgets with exponential backoff math. This final example integrates 3 constraints: total attempts, total elapsed time, and a backoff schedule with a maximum sleep. It shows how to compute the next sleep while checking the remaining time budget and remaining attempts. It also demonstrates aborting early when either budget is exhausted. Tuning the attempt cap, the total time, the initial backoff, and the cap directly changes behavior. Increasing total time allows more retries. Raising attempts increases cost. Increasing initial backoff slows retry frequency. Recap. What it is: a disciplined retry policy that enforces max attempts, max time, and a bounded backoff. When to use it: whenever you call unstable services and need predictable latency or cost. One caveat: tight budgets can cause premature failures, so tune against realistic failure patterns. Next step: try this exact pattern against a real unstable API and collect timing and success rates. Then, tune the attempt count, total time, and backoff cap based on those measurements. If short, practical AI engineering helps, subscribe and watch the AI engineering videos.